Swayam Prabha. Digital India. Educated India.
Okay, and as I already mentioned, our interest in generating functions is because you can get them from recurrence relations. So let's take an example. This is a Fibonacci sequence, and the recurrence relation, these are the base cases, f0 and f1, and fn is fn minus 1 plus fn minus 2 for n greater than or equal to 2. Okay, now imagine you take this recurrence relation and imagine multiplying it by the capital X to the power n on both sides of the equation. Okay, and I've rewritten, so here it's fn minus 1 times x to the power n. I've rewritten it as fn minus 1 to the times x to the power n minus 1 times x, and similarly fn minus 2 times x to the power n minus 2 times x squared. Okay, and what does this let me do now? Imagine I sum this up for the formal summation for all n greater than or equal to 2, and I want to see what the generating function looks like, or how it shows up when I do the summation. So this is not quite the generating function here, right? Because the summation here is from n greater than or equal to 2, whereas the generating function is from n greater than or equal to 0. And here, same thing, but here actually this is the generating function, because I said n greater than or equal to 2, but I'm doing f of n minus 2 times x to the power n minus 2. So if you substitute variables, you say k equals n minus 2, then the summation k greater than or equal to 0, fk x to the power k. Okay, and that would be the generating function. So this entire summation here is simply the generating function of f. And out here and here, it's almost the same thing. It's just that it's missing a couple of terms. So the one here is actually gf of x without the first two terms. So I just write this as gf of x and subtract out the first two terms. So f0 plus f1 times x to the power 1. Okay, and here x times what is in the summation is gf of x minus f0. So that's because the summation is, if you do a substitution of variables, k equals n minus 1, this is summation is for k greater than or equal to 1, fk x to the power k. So that is just missing the term f0 from gf of x, right? So what's in the summation is gf of x minus f0. And here, as I already said, is all of gf of x. Okay, so I can write this equation now, which is all in terms of gf of x. Okay, and then by rearranging all the factors involving gf of x, so here is an x times gf of x, here is an x squared times gf of x, so they come to the other side. So it's gf of x times 1 minus x squared, and I take everything else to the other side, is equal to f0 plus f1x plus f0, sorry, minus f0x, right? So that's on the right hand side. In other words, it gives me that gf of x is, so I'm substituting the 0 and 1 here. So this f0 goes away, f1 minus f0 is just 1. So it is x on the right hand side. So this is x divided by 1 minus x squared. Okay, that is the generating function for the Fibonacci sequence. More generally, if you had, instead of 0, 1, if you had some number CD, and instead of this combination being 1 times fn minus 1 plus 1 times fn minus 2, if you had some coefficients a, b, the same derivation goes through, and you would get gf of x as, so there will be something involving x and a constant term. divided by something instead of 1 minus x squared, it will be 1 minus ax minus bx squared. Okay, so you can derive this yourself. And so that's a generating function for a more general recurrence relation, from which we'll see shortly you can get the closed form, which we already did in a previous video where we proved it inductively. Okay, so we'll get to that, but let me finish with one more quick example of where do you get generating functions from. So suppose there are two sequences. There is a sequence f, which somehow you are defined separately, and now suppose there's another sequence g that you're defining in terms of f simply as, so gk is f summed up to k, so j equal to 0 to k fj summation is what gk is. Okay, so gk is simply summing up fk minus 1 all the way to f0. Now, could you write the generating function of g in terms of the generating function of f? Because that would give you more power in terms of how to what all can have nice generating functions. Whenever f has a nice generating function, could you turn it into a nice generating function for g, so that whenever you have a closed form expression for f, hopefully it'll translate to a closed form expression for g. So let's see what we can do. So let's rewrite this summation as a recurrence relation. So I would say, okay, g0 is f0, and gn for all larger values of n is simply gn minus 1 plus fn. So you need to add fn, to the sum up to fn minus 1. You add fn, you get the sum up to fn, right? So that is gn. So now we have a recurrence relation, and we could do what we did in the previous slide and multiply this equation by some formal variable x to the power k, and so here you'll have fk times x to the power k. Okay, but this is true only for k greater than or equal to 1, right? This equation is only for k greater than or equal to 1. And now you sum this for k equal to 1 to infinity. And what you have is, so I rearrange things a little bit. So here, this is pretty much the same as the generating function of x, but it is missing one term, namely g0, and sorry, which I have taken to the other side. And this one is exactly g generating function for little g, but it's multiplied by x, so it will be x times ggx. And this one again is a generating function for f, all of it except k equal to 0, right? So you have minus f0 here. Okay, and now you rearrange the terms. What you get is, so we have g0 and f0 are equal, so they cancel off, and you're left with you take this to the other side, you get 1 minus x times gg of x equals gf of x, or in other words, gg of x is gf of x divided by 1 minus x. Okay, so you might get a rational polynomial kind of expression if gf already has such an expression. Okay, so indeed you can go from generating functions of f to generating functions of g if g is defined as a summation of f. Okay, so we'll see a few more examples in the next video. I'll stop here for now. So we'll see some more examples of generating functions and how to use them. So to recap, generating functions, we define them for a sequence of real numbers, or we could think of it as a function from integers to real numbers, so f0, f1, and so forth. And its generating function is this formal expression where it's capital X as a formal variable. You could think of this as a polynomial of infinite degree, where the coefficients are the values that this function takes, so the values in the sequence. And where do these generating functions come from? So one source of generating functions is the extended binomial theorem. So for instance, for um, an expression of this form, so this is 1 minus ax to the power minus b, so where b is a positive integer. And the extended binomial theorem can be used to get the coefficient for x to the power k in this form, which I have further rewritten. Um, so I had a minus a here, so there's a minus 1 to the power k, and these are k negative integers, minus b minus 1 all the way to minus b minus k plus 1. So the minus 1 to the power k cancels off with the signs of all these k integers in the numerator, and you can verify that what will be left to it is this expression. Okay, so there's an example of the extended binomial theorem. So that gives generating functions for a certain class of functions. You could get more generating functions for more functions by combining various generating functions. For instance, if your function is of the form f plus g, then its generating function is simply the sum of the generating functions of the of f and g, because the coefficients of x to the power k add up in these two expressions. You could also, of course, you could also multiply by constants. You could also multiply by powers of x. So for instance, if you multiply g of x by x, or a constant times x, what you have is a generating function for another function which shifts the indices by 1. So g0 becomes 0 because there's no constant term in this expression. And g1 is the same as f0 times alpha. So gk more generally is alpha times fk minus 1. So it just shifts f by 1 position. You could also then combine these two. For instance, you can define a generating function of f times 1 plus alpha x as a generating function of h, where h is simply fk plus gk, where gk is alpha times fk minus 1. Right. So yeah, once you have a few generating functions, you can put them together to build generating functions for other sequences. But our main source of generating functions, and the examples we'll see some of them today, are from recurrence relations. So an example, this is a class of recurrence relations for, say, the Fibonacci series is an instance of this, with a and b equal to 1. And the generating function for such a recurrence relation we saw last time, you can derive as, you can pretty easily derive as something of this form. Okay? We also saw another example where you define one function in terms of the summation of another sequence, and then you can derive the generating function for this g in terms of generating function for f in this form. Okay. So these are all examples we saw so far. Let me start with an example of this last type. So I define gk as a sum of fj, where fj is j plus 1 square. Okay, so gk is the sum of fj, j equal to 0 to k. So this is simply the sum of the first k k plus 1 integer. So j goes from 0 to k, you're summing 1 square plus 2 square up to k plus 1 square. So gk is just defined as the sum of the squares of the first k plus 1 integers. I've called it gk rather than gk plus 1 for convenience in the derivation I'll show you now. So what we are interested in is in getting a closed form expression for this, which you might have seen earlier, but let's see how you derive it rather than just prove it. So the generating function for this, from what we saw earlier, is just g of x divided by 1 minus x, where g of x is a generating function for f. So let's figure out what the generating function for f is. This is something you can get from the binomial, extended binomial theorem and the combinations, but let's arrive at it kind of more directly. So we'll start with something simple for the that we know from the extended binomial theorem, which is the generating function for 1. So this is just 1 plus 1 times x plus 1 times x squared and so forth. And the binomial, the extended binomial theorem tells us that this is 1 over 1 minus x. What I'm going to do is, suppose I take the derivative of this infinite sum, right? So, so it's a little bit, of calculus, right? Which you wouldn't expect to see in a discrete structures course. But for now, let's just go ahead and treat it as just a formal mechanism. We'll apply the rules of derivations to each of these terms in a formal sense. So x to the power k will become k times x to the power k minus 1. The 1 here disappears when you take the derivative. X became 1, x squared became 2x, and so forth. So that's the summation here. On the right hand side, again, you can use the rules of derivation to directly get that this is 1 divided by 1 minus x, the whole square. Okay. And this would indeed be, would make sense in calculus for small enough x's. But we are going to, this is just something we could have derived from the extended binomial theorem, which also we are using as a black box. Right, if you applied, if you just expanded 1 divided by 1 minus x the whole square, so 1 minus x to the power minus 2, using the extended binomial theorem, this is exactly what we would get. And we saw this. But let me, continue manipulating this expression by doing a formal application of derivatives. So before that, so what am I interested in? I would like to get something of the form k square to the k square times x to the power k, or x to the power k minus 1. So what I'm interested in is in getting, here it's something like k times x to the power k minus 1. I'm interested in getting something like k squared times x to the power k minus 1. So I could take derivative once more, but then I'll get k times k minus 1, right? 3 times 2, which is not what I want. I want 3 times 3. So I'm going to just multiply this expression once more, once by x, so shift everything as it were. So multiply by x so that now this term becomes 3 times x to the power 3, or more generally k times x to the power k. Okay, so I did the multiplication on the right hand side also. And now I take the derivative once more, and I would get k squared to the power x over k minus 1. And this k squared is what I wanted. So on the right hand side, if I take the derivative, it simplifies to 1 plus x over 1 minus x cubed. And this is a generating function of fj is j plus 1 square. Right, so this is j plus 1 square times x to the power j. And this is indeed, and now, so I have the generating function for f, and I have the generating function for g now from this formula. So it is 1 plus x divided by 1 minus x to the power 4. Okay. So uh, you know, uh, got the generating function, and now how do I get the closed form? Well, this, is 1 divided by 1 minus x to the power 4. You can use the extended binomial theorem to get its the coefficient of x to the power k, and same you can do with x divided by 1 minus x to the power 4. You can use the extended binomial theorem, and then you can add this. So I'll leave it as an exercise to use the extended binomial theorem to compute the coefficient of x to the power k in this, and that would give you a closed form for this summation. Okay, let me show you another example, which again is something you have seen before. So here is a counting question that we have asked before. How many ways can you throw n unlabeled balls into d labeled bins? Uh, Here I'm going to think of n as a variable. So I'm defining this function. This is a function of n, the number of ways you can throw n unlabeled balls, into some fixed number of bits. Okay, so it's just a function of one variable. And we already saw the solution for this using stars and bars. You can assemble d minus 1 bars and n stars. That's the number of ways you could choose. That's the solution for this. But let's see another solution now by reasoning about the generating function of this sequence. Okay, so we are interested in, so what should gf of x look like? It has coefficients fn for x to the power n. So for x to the power n, you want a coefficient which is counting the, so when you throw the n balls into d bins, the numbers be n1, n2 up to n to the nd, and they should add up to n, right? You have to throw all n balls into the d bins. The bins are labeled, so first bin, second bin, up to d. So this number fn is the number of non-negative integer solutions to this. So that's what you would like to show up as the coefficient of x to the power n. And that is indeed the case if you took, if you looked at this expression. So this is an infinite sequence, 1 plus x squared all the way to the power d. Now if you thought of the coefficient of x to the power n in this product, so there's a product, each term of the form x to the n comes from picking one term each from each of the factors here, and the powers you picked from each of the terms here would be the n1, n2, and so forth, and they add up to n. That's why they multiply to x to the power n. And the number of ways you can do this is exactly the number of the coefficient of x to the power n in this expression. Okay, so this is a generating function for f, and you can simplify this now, right? Instead of writing 1 plus x squared ad infinitum, you can apply the extended binomial theorem and write this as 1 over 1 minus x. So generating function is 1 minus x to the power minus d. And now you can apply the extended binomial theorem again to get the coefficient of x to the power k in this expression. Okay, and it's, and that is, as you saw just a while back, d times d plus 1 times and so forth n terms divided by n factor. That's just d plus n minus 1 choose n. And this is exactly what you would get from using n bars, n stars, and d minus 1 bars. Okay. Now let me show you one more application which can be again saw earlier. We saw the closed form for this recurrence relation, and we saw two forms of it depending on whether this characteristic equation here has two solutions or one solution. But the way we saw this is I pulled this claim out of nowhere, and then we proved it by induction. So what we're going to do now is actually see how to arrive at this expression using generating functions. Okay, so I'll start off with, so we already seen the generating function for this. So let me write that down here. And then the goal is to derive a closed form expression for the coefficient of x to the power k. So just for convenience, I will, instead of this expression d minus ac, I'll just call it beta, and the first one I'll call it alpha, so that we get similar. So the expression I'm interested in is some alpha plus beta x divided by some quadratic expression x. Okay, and this is not quite the characteristic equation. Um, so I can rewrite this in terms of 1 over x. So do a substitution of variables. So g of x I can write in this form where z is 1 over x. Okay, so this is just a formal variable substitution. And the reason I'm going to do this is because the two cases that we are interested in would be in terms of the solution of this quadratic equation. Okay? So we can always factorize a quadratic expression over complex numbers as a multiple of two linear expressions. So z minus x times z minus y, where a is x plus y and b is minus b is x times y. And and I can go back to writing this in terms of capital X, my original variable. So there's just saying that this expression here is 1 minus x times 1 minus y times x. So little x and little y are some two complex numbers. But there are two cases depending on whether these two these two solutions are equal or not equal. Okay? So this is just summarizing what we had in the previous slide. We're given a generating function of this form where little x and little y are such that they are the two solutions that we are interested in. So a equal to x plus y or minus b equal to x y. Okay, and the two cases. So let's first consider the case when x not equal to y. In this case, I will factorize this 1 divided by 1 minus x times 1 minus yx in this form. So this 1 divided by 1 minus xx minus 1 divided by 1 minus yx. If you expanded this, you will see in the numerator, so the denominator will be this, and the numerator you will get xx minus yx. So I'm going to divide by that, xx minus yx, so that I've taken the capital X out. Okay, so and this requires for me to be able to write this and not get a 0 divided by 0 form. I needed x not equal to 1. Okay. Now each of these things I can expand using the extended binomial theorem. So 1 minus xx, to the power minus 1 is 1 plus xx plus xx square, the whole square, and so forth. And similarly for yx, right? So I just plug that into the expression here. So I have alpha, and there is a divided by x times x minus y. So that's why I have an alpha divided by x plus beta divided by x minus y times the summation xx to the power k minus yx to the power k corresponding to this. Okay, so this is my generating function for x, and now I'm interested in the coefficient of x to the power k. This, as you can see, this beta would just give me x to the power k minus y to the power k times beta divided by x minus y. Here there will be a shift of variables. So I'll get x to the power k minus 1. And for the sake of grouping terms properly, I'm going to write this as x times x to the power k minus 1. So this alpha divided by x, made this x little x to the power k, capital X to the power k minus 1. So I'm writing it as little x times little x capital X to the power k minus 1. Similarly, minus y times yx to the power capital power k minus 1. Okay, so that's from the alpha divided by x, and the beta thing there is no such shifting. And here, my summation I kept from k greater than or equal to 1, because anyway for k equal to 0, this thing was 0. Right? This is just 1 minus 1. So this I will do a substitution of variables. So this will also become some k greater than or equal to 0, and here will be x to the power k, so that I can combine it with this. But instead of so here I have beta, here I'll have alpha x and alpha y. Okay, so if I group the terms, coefficients of little x to the power k, I would get it to be of the form p times little x to the k, capital X to the power k, where p is alpha x plus beta divided by x minus y. And similarly for little y to the k, I will get the coefficient this one. And so Fn is the coefficient of x to the n in the generating function, which is indeed px to the power n plus qy to the power n. And if you substitute the values for alpha and beta, you'd get back the expression that we originally had. And the case for x equal to y is somewhat similar. So in this case, instead of 1 minus xx times 1 minus yy, you have 1 minus xx the whole square. But you can use the binomial theorem again to expand it. And now there is an extra factor of k in the expansion. And when you plug it in, that factor of k shows up. So you collect all the terms that involve that k, and so that will be, so there will be a term from alpha, there will be a term from beta, and that will be of the form alpha plus beta over x. So I'll leave it to you to verify this. But again, this is exactly the same expression we used and proved it inductively. But now we have arrived at it using the extended binomial theorem and the generating function. Okay, so one last example I want to show you is of Catalan numbers. Again, we had an interesting recurrence relation for Catalan numbers. And what we'll do now is use generating functions to find a closed form expression for Catalan numbers. Okay, so that's recurrence relation for cat n. And we are interested in finding the generating function. So one term of this generating function would be of the form cat n times x to the power n. So you can just multiply this by x to the power n. This holds for n greater than or equal to 1. Now, what is this expression? So I'm saying you could instead think of this as the term containing x to the power n in this product, okay, which is the same as term containing x to the power n minus 1, or the coefficient would be the same as that of x to the power n minus 1 in this product of these two terms. And what is that? So I've written it as the summation is for k greater than or equal to 1, and the summation is k less than or equal to 1. Here the power is x to the power k minus 1, here x to the power n minus k. The term containing x to the power n minus 1 would be to pick for any k, but the same k, the term from here and term from here, you multiply them, you will get x to the power n minus 1. So that's the only way to get x to the power n minus 1. So the coefficient would be go over all k that is here and multiply the two terms. So that's exactly what's happening here. The product is for k equal to 1 to n, because if you have to find a k here and a k here, it has to be both greater than or equal to 1 and less than or equal to n. So it's in this range. Okay, and cat k minus 1 times cat n minus k times x to the power n minus 1 is what you would get from here, sum over all k, and times x would give you x to the power n. Okay, so you should convince yourself this term is exactly what appears as the term containing x to the power n in this product. That is for n greater than or equal to 1. For n equal to 0, clearly there is no term containing x to the power 0 here, because everything has x to the power at least 1. But we can add that in separately. For n equal to 0, cat 0 x to the power 0 is simply 1, because cat 0 is 1 and there is no x term. Okay. So now the generating function is simply this thing added up for all n, but here this quantity is already summing over all x to the power n. So it's all the terms for all n greater than or equal to 1 is already accounted for here, and then you just need to add this. And what is this? Well, each of this is actually the same as the generating function for Catalan numbers, right? So here k greater than or equal to 1, the range is such that this goes for Catalan 0 x to the power 0 all the way to infinity, and here also it's the same thing. Okay, so here k goes negative, and that accounts for all powers of x, or positive and 0 powers of x. So these are both the same as the Catalan, the generating function for Catalan numbers. Okay, so we have this identity for the generating function. So remember, the generating function is an infinite formal series, and we just argued that it should satisfy this condition. That still doesn't immediately give you the give you a nice expression for the generating function, but you could think of this as a quadratic equation where we are trying to find out what this term is, this g cat x. So just writing that as g, the quadratic equation is saying g equals 1 plus x times g squared, or I've written it as x times g squared minus g plus 1 equals 0. If you solve for this for g, it's a quadratic equation, you get two possible solutions: 1 plus or minus square root 1 minus 4x divided by 2x. Okay, there's some sort of a rational expression. But there are two of them. Which one should we take? So we could look at what this should behave for some specific value of x. So let's try x equal to 0. Now there's a divided by 0 here, so that wouldn't let us evaluate this expression. However, we can take the limit as x goes to 0. So we'll again use some calculus here. So we know what g cat x should go to when x goes to 0. It goes to cat 0. All the other infinitely many terms go to 0, and assuming that they would converge to 0, what you would have, you're left with is Catalan 0, which is 1. So you want this expression when x goes to 0 to be 1. So let's figure out what that limit is. So you'll need to apply a rule from calculus to compute this limit. So you could do the L'Hopital's rule, take the derivative with respect to x in the numerator and denominator, and you would get that depending on the sign plus or minus, you would get minus or plus 1. Since we are interested in the limit being plus 1, you would want to take the sign here to be minus. So we will take um, this solution, 1 minus square root of 1 minus 4x divided by 2x, and we'll go ahead and, so if at all there is an expression for Catalan, the generating function, uh, it has to be 1 minus square root 1 minus 4x divided by 2x, not 1 plus square root 1 minus 4x divided by 2x. And at the end we can verify that by this trickery we didn't get some wrong solution. So you can verify the solution once we finish with this analysis. Okay, so the question is, okay, so let's we have a candidate for the generating function, but we are interested in a closed form for the Catalan number itself. So what is the coefficient of x to the power n in this expression? That's what we are interested in. That's cat n. Okay. Okay, so just to repeat that. So this is a generating function, and we are interested in the coefficient of. So I'll write x to the power k here. Okay. Okay, so how do we do this? Again, we would like to use the extended binomial theorem, but now we have for the first time in our examples, we have something with a non-integer power. Okay, so 1 minus 4x to the power half. So let's just focus on that for a second, expand that. So 1 minus 4x to the power half. This is what the extended binomial theorem tells us. It's exactly minus 4x to the power k and half choose k for k summed over all k greater than or equal to 0. For k equal to 0, this half choose k is just 1. So this term will be 1. But for k greater than or equal to 1, let's expand this and see what it looks like. So for k greater than 0, so half choose k, remember in the extended binomial theorem, that means half times half minus 1 times k terms, and then divided by k factorial. So half times minus 3 by 2. So the numerator here would increase by 2. The negative number would increase by 2 each time. So if you just rearrange this, so you have the first term is positive, but then you have k minus 1 negative term. So you have minus 1 to the power k minus 1. The numerators are 1, then 1, 3, 5, and so forth. So there are k minus 1 of these odd numbers. So the last one is 2 times k minus 1 minus 1. So that is 2 times 2k minus 3. And then there are k of these divided by 2. So I have a 2 to the power k in the denominator in addition to the k factorial that is already there. So what is this quantity? Well, we can simplify this a little bit by, I fill in all the missing even terms here, 2, 4, all the way to 2k minus 2. And I divide by them as well. So I multiplied the numerator and the denominator. But in the denominator, I will write this a little differently. So these are all even terms. So I take the factor 2 out of them. So that is just 2 to the k minus 1. And I'm left with 1, 2, 3 up to k minus 1. So that's k minus 1 factorial. Okay. Now what does the numerator look like? It looks like 2k minus 2 factorial. Right, all the even and odd terms are here. So 2k minus 2 factorial divided by, so if this was also k minus 1 factorial, then I can write this 2k minus 2 factorial divided by k minus 1 factorial times k minus 1 factorial as 2k minus 2 choose k minus 1. Right, so this is 2k minus 2 factorial divided by k minus 1 factorial times k minus 1 factorial. But this was actually a k factorial, so I'm left with an extra term k in the denominator. There was already a 2 to the power k. I have now 2 to the power k minus 1, so I have 2 to the power 2k minus 1. Okay, so this is half choose k. Now putting that back in here, so this for k greater than 0. for k equal to 0, we have the 1. And for k greater than 0, we have this quantity from here times minus 4 to the power k times x to the power k minus 4 to the power k here, so minus 1 to the power k here, and minus 1 to the power k minus 1 here leaves you with a minus 1. So there's a minus, and this is 4 to the power k. In the denominator, we do have 4 to the power k divided by 2. So that we are missing a factor 2 in the denominator, so that shows up as a factor 2 in the numerator. And there's this divided by k. So this is the final expression for square root of 1 minus 4x, 1 plus summation k greater than or equal to 1, this quantity with x to the power k, its coefficient being this. Okay. And now I can substitute this back into the full expression for the generating function. And I'm interested in 1 minus this quantity divided by 2x. So that would be just this part without the minus divided by 2x. So the 2 goes away and divided by x. So instead of x to the power k, I will have x to the power k minus 1. Okay, and the summation is for k greater than or equal to 1. Now, as you can now, so we want to find cat k, which is a coefficient of x to the power k in this thing. So by substituting variables, for summation k minus 1 greater than or equal to 0, right? So take this k minus 1 to be k. What you have is 2k choose k divided by k plus 1 times x to the power k. That's what the summation is over, right? So at the end of all this, we have a very nice expression for Catalan number cat k, just 2k choose k divided by k plus 1. And now you could verify this if you want by induction, by substituting this into the recurrence relation. Okay, so I'd leave that as an exercise for you. Okay, so that's all I had to say about the generating functions and their applications, but there are several more examples of using generating functions, and we have restricted ourselves to ordinary generating functions. There are many cases where the exponential generating functions are also useful. So it's a very useful trick to have in your toolkit.